You have learned that when a multi-engine aircraft suffers an engine failure, there are several variables which affect both the yawing moment and the rudder moment used to oppose it. You have also learned that there is a minimum IAS, VMC, below which it is impossible to maintain directional control under asymmetric thrust. Airworthiness authorities, the one quoted in this lesson being the JAA, have laid down conditions to be satisfied in establishing the minimum airspeeds for inclusion in the flight manual of a new type. In most instances, the conditions are based on a worst case. A safety factor is built into these speeds to allow for aircraft age and the response time of an average pilot. Because there are distinct variations in an aircraft's handling characteristics in certain configurations and stages of flight, minimum control speed, VMC, has three separate specifications, which are VMCA, the minimum control speed in the air, VMCG, the minimum control speed on the ground, and VMCL, the minimum control speed in the landing configuration. For aircraft with 3 or more engines, airborne speeds will also be defined for single and double engine failures, nominated VMCA1 and VMCA2, and so on. The JAA and its successor, EASA, specify the parameters for determining VMCA. Here we have paraphrased the JAA requirements as laid down in Regulation JAR 25.149. VMCA is the calibrated airspeed at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the aeroplane with that engine still inoperative and maintain straight flight with an angle of bank of not more than 5 degrees. VMCA may not exceed 1.13 times the reference stall speed under these conditions. Maximum available takeoff power or thrust on the engines, the aeroplane trimmed for takeoff, the most unfavorable center of gravity position, maximum sea level takeoff weight, the aeroplane in its most critical takeoff configuration, but with gear up, the aeroplane airborne and the ground effect negligible, and, if applicable, the propeller of the inoperative engine either windmilling or, if an automatic feathering device is fitted, feathered. The rudder control forces required to maintain control at VMCA may not exceed 150 pounds, nor may it be necessary to reduce power or thrust on the operative engines. It should be noted that no performance requirements are specified. The only necessity is directional control. There are several factors that affect VMCA. They are as follows. Banking towards the live engine reduces the rudder deflection required, and so allows a lower VMCA. 5 degrees is stipulated because larger bank angles would significantly diminish the vertical component of lift, requiring a higher angle of attack with its attendant drag penalty. The position of the CG, around which the aircraft rotates, will directly affect the length of the rudder arm, and thus the power of the fin and rudder to give directional control and stability. The worst case is with the shortest arm, the CG being at its aft limit. As well as the rudder, the aileron's effectiveness is reduced at lower airspeeds, requiring greater deflection to keep the wings level or hold the required bank under asymmetric power. If the down aileron deflection is large at low speed, it may be enough to cause a stall of that wing, giving an uncontrollable roll towards the dead engine. VMCA must be high enough to avoid this situation. Flap position affects the lift-drag ratio, nose-down pitching moment, and stalling speed. With asymmetric thrust, flap reduces climb rate whilst increasing the margin above the stall, but does not directly affect VMCA. However, if takeoff flap is used, there will be a greater difference of slipstream-associated lift between wings, giving a larger rolling moment, needing more aileron, and indirectly increasing VMCA. The undercarriage increases drag and reduces performance. The extra keel surface in front of the CG slightly reduces directional stability, opposing the fin and rudder, with a small increase in VMCA. Increases in altitude and temperature will reduce the thrust from the live engine or engines unless boosted, and VMCA will be reduced accordingly. The relationship between stalling speed and VMCA can be seen on the graph on screen, in which the VMCA curve intersects with VS, typically around 3,000 feet. Thus, above this altitude, an aircraft would reach the stall before VMCA on deceleration after engine failure. This gives a smaller speed margin above loss of control. JAR Regulation CS 25.149 gives the parameters for ground minimum control speed. It states that VMCG is the calibrated airspeed during the takeoff run, at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the aeroplane with the use of primary aerodynamic controls alone, that is, without the use of nose-wheel steering, to enable takeoff to be safely continued using normal piloting skill. The rudder force may not exceed 150 pounds or 68.1 kilos, and until the aircraft becomes airborne, the lateral control may only be used to the extent of keeping the wings level. In the determination of VMCG, assuming that the path of the aeroplane accelerating with all engines operating is along the centre of the runway, its path from the point at which the critical engine is made inoperative to the point at which recovery to a direction parallel to the centre line is completed may not deviate more than 30 feet or 9.144 metres laterally from the centre line at any point. As with VMCA, these conditions must be established with maximum available takeoff power or thrust on the engines, the aeroplane trimmed for takeoff, the most unfavourable CG position, and maximum sea level takeoff weight. There are several factors that affect VMCG. They are as follows. As with VMCA, increases in altitude and temperature will reduce the thrust produced by the live engine or engines if unsupercharged, and VMCG will be reduced accordingly. Nose wheel steering is designed for taxiing, making tight turns at low speed, turning off the runway, parking, and so on. When taking off on wet, icy or slippery runways, the nose wheel can lose adhesion and have little steering effect. VMCG is established during flight testing, usually on a dry runway. If the test pilot were to use the steering, it would give a false low control speed, which could result in loss of control if used in emergencies. The regulations are established according to worst-case parameters, to give the maximum safety factor. The rudder arm, when the aircraft is on the ground, is shorter than when airborne, as it rotates around the main undercarriage, which is aft of the CG. On most aircraft, therefore, VMCG will be higher than VMCA.